Hello friends, in this lecture we'll discuss regarding poles. In the last two lectures we have discussed regarding singularities. Singularities, it's a classification that is isolated singularity, non-isolated singularity, and in isolated singularity we have seen removable singularity. Removable singularity. Okay, now we'll go for poles. A point z0 is called a pole of a function f of z if z minus z0 to the power n f of z is bounded near z0 for some n belongs to integers, for some integer n. So what is the poles here? The point z0 is called a pole of a function f of z if z minus pole of order n now. Pole of order n or pole first of all if this z minus z0 to the power n of f of z is bounded. Bounded means what? As z tends to z0 of this function it is equal to something L. The limit should be constant or limit of this function exists. Is bounded for n belongs to z. The smallest positive n such that z minus z0 to the power n of f of z is bounded near z0 is called, if this holds, then z0 is called pole of order n. So if there exists a smallest integer n such that mod z minus z0 to the power n of f of z is bounded near z0, then this z0 is called pole of order n. Z0 is called pole of order n. Now what this means? This exists means what? There should be f of z upon z minus z0 to the power some m where m greater than n. Such kind of situation is there that after multiplying it, this should be vanished and it is equal to m less than n should be there. This should be vanished. Then it is called pole of order n. Pole of order n. A pole of order 1 is called a simple pole. That means what? If z minus z0 of f of z is bounded near z0, then z0 is called pole of order n. No doubt pole is also again a singularity that can be removed by using this one. Okay, that is the case. For example, the function f of z equal to z to the power 8 upon z minus 1 square has a double pole at z equal to 1. Now see this function. Now we know that this function has a singularity at z equal to 1. Right? It has a, which singularity then? Isolated. Singularity is what? Isolated singularity, no doubt. Because except z equal to 1, this function is analytic everywhere. That function is analytic everywhere. Okay, that is the case there. Now, we can remove the singularity by redefining this function and finding limit of this function. Right? Finding limit of this function as z tends to z0. If it exists, then we call it as removable singularity. Okay, that is one matter, another matter. So now we will see what about pole of order which one. So here, if I take limit as z tends to 1, z minus 1 square into z raised to 8 upon z minus 1 square, then these two cancel. So we get only limit as z tends to 1, z to the power 8, that is 1. So this is exist and it is bounded. That is z minus 1 square into z raised to 8 upon z minus 1 square is bounded near z equal to 1. Is bounded near z equal to 1. That is limit exists and therefore this function has a pole of order 2 at z equal to 1. Function has a pole of order 2 at z equal to 1. Similarly, the function 1 upon 1 plus e to the power I pi z has a simple pole at z equal to 1 plus 2k and z equal to infinity is the limit point of these poles. What we are saying, the function f of z which is given by 1 upon 1 plus e to the power I pi z has a simple pole at z equal to 1 plus 2k and z equal to infinity is the limit point of these poles. Is the limit point of these poles. Now we'll show it. Now here this function has an has a singularity at which 1 plus e to the power I pi z equal to 0. So let 1 plus e to the power I pi z equal to 0. This implies e to the power I pi z equal to minus 1. Now e to the power I pi z equal to minus 1, that can be written as e to the power I pi into e to the power, we want to prove e to the power I pi into e to the power z, e to the power 2k I pi for k belongs to z, and this can be written as e to the power 1 plus 2k I pi, k belongs to z. Now why we can write e to the power I pi z is equal to minus 1? We know that e to the power I pi z minus 1, we know that e to the power I theta is what? E to the power I theta is cos theta plus I sin theta. Now when this will be, I times theta will be e to the power I theta is minus 1. When this will be minus 1, for which value of theta it is minus 1? We can say that, now see here, if I take theta is equal to 0, then this becomes 1. If theta is equal to pi by 2, then this becomes I. If theta becomes pi, it becomes minus 1. Theta is pi, then it becomes minus 1, e to the power I pi, cos pi plus I sin pi. Similarly, for 2 pi it is 1, for 3 pi it is minus 1, for 4 pi it is plus 1, for 6 pi, that means what? If your theta is pi, 3 pi, 5 pi and so on, then e to the power I theta is minus 1. In the same way, if pi z is equal to either pi or 3 pi or 5 pi or 7 pi etc., that is odd multiples of pi. If your pi z is odd multiples of pi, if pi z is odd multiple of pi, then e to the power I pi z equal to minus 1. If pi z is odd multiple. What this implies? Pi z is odd multiple of pi means pi z can be written as 1 plus 2k into z. Pi z can be written as 1 plus, right, into pi. Then these are all odd multiples of pi, because if I put k is integer, 2k is even and its plus is odd multiple. Therefore, if your pi z is odd multiple, that means your z should be 1 plus 2k. And therefore, that z is equal to 1 plus 2k is a singularity of this function. Now we will say that it is singularity means pole, no doubt. So what is the order of this pole that we want to go? So order of this pole, to obtain the order of this pole, we have to find now this limit. Limit as z tends to 1 plus 2k, z minus 1 plus 2k into 1 upon 1 plus e to the power I pi z, because we have to take this point. So limit at z tends to 1 plus 2k of, what will happen here? If I take z equal to 1 plus 2k, this is numerator is 0, denominator is also 0. So 0 by 0 form. We know that 0 by 0 form using L hospitality rule. Numerator, its a derivative of numerator is 1 with respect to z, and derivative of denominator with respect to z is I pi into e to the power I pi z. Because of this, actually this form is 0 by 0. This is not 0 by 0. This form is 0 by 0. That's why we have taken. Now take z tends to 1 plus 2k. So now numerator is not 0. So I pi e to the power I pi into 1 plus 2k, which is equal to 1 upon minus I pi, which is equal to I upon pi also. Why we get minus I pi? So here I is there, pi is there, and what about this? We know that this is minus 1. E to the power I pi into 1 plus 2k. E to the power I pi into 1 plus 2k is what? Odd multiple of pi, so it should be minus 1. So minus 1 into this one. Divide multiplying numerator and denominator by I, you will get I upon pi. What is it? It is finite. It is finite. Means what? Z minus 1 plus 2k into 1 upon 1 plus e to the power I pi z is bounded near z equal to 1 plus 2k, and therefore this z equal to 1 plus 2k is a pole of one order, that is simple pole of this function, Similarly, we have this example also. Consider the function f of z equal to z times cos of pi z upon 2a upon z minus a z square plus b square to the power 7 sin raised to 5z. Now for which values of z this denominator is 0? Number 1 at z equal to a. Number 2 at z equal to z square plus b square. Z square plus b square is 0 means what? Z square equal to minus b square, that is z equal to plus or minus ib, and then z at z equal to 0, then at z equal to 0. So z equal to 0 is a singularity, z equal to plus or minus ib is also a singularity, and z equal to a is again a singularity. Now we will verify that z equal to a, whether it is a pole of order which. Similarly, z equal to ib and z equal to 0, where a, b are distinct non-zero real numbers. Here limit as z tends to a, I will find z is z cos pi z upon 2a upon z minus a into z square plus b square sin raised to 5z. So limit as z tends to a, cos pi z by z, z minus a by z, z square plus a square sin raised to 5z. Isn't it? Limit at z tends to plus or minus ib. Okay. What is happening here? Z tends to a, cos pi by 2. Okay. Z equal to a. A cancel cos pi by 2 upon z minus a by z. Okay. Z square minus z square plus a square. It is equal to a square. Sin raised to 5z. And z tends to a. This becomes 0 by a. So it becomes infinity. Okay. It becomes infinity. So it is a singularity. Now, can I say as z tends to a, what about this? As z tends to a, this is not 0 by 0 form. So this limit is 0. So denominator is 0. A square plus a square. It is again 0. Sin a will be there. Now, if I take z minus a, then what will happen? This z minus a cancels with z minus a. And if I put z equal to a, then this becomes, this is 0 by 0 form. Cos pi by 2 is what? 0. And this is also 0. Okay. Cos pi by 2 is 0 and this 0 by 0 form I get. If I take its derivative again, then it will be some other way. What about derivative of this term? This is 0 by 0 form. If I take derivative, z into sin pi z by 2a into pi by 2a minus plus only cos pi z by 2a whole divided by derivative of this term, that is u into v into w formula. First function as it is, second function as it is, derivative of 5 into sin raised to 4z into 1, no need to write, plus these two functions as it is and this one. So z equal to a is a simple pole here. Z equal to a is the simple pole, because if we find the limit as z tends to a of z minus a into this one, this will be finite. Now I am finding limit as z tends to plus or minus ib, z square plus b square to the power 7, right? Z square plus b square to the power 7. You get z into cos pi z upon 2a, z minus a, z square plus b square to the power 7 sin raised to 5z. These two will be cancelled. We get z is plus or minus ib, cos plus or minus I pi b upon 2a, and this holds plus or minus ib into cos of this one. Only we have put a value of z as plus or minus ib. So this is finite. Now this is finite. Okay. Therefore, fz has a pole of order 7 at z equal to plus or minus ib. Z equal to a is a pole of order 1. right? And now lastly, limit as z tends to 0, we are multiplying by z raised to 4 here. Z raised to 4 into z into cos pi z by 2a upon z minus a z square plus b square to the power 7 z raised to 5z. Okay, so z raised to 5 upon z raised to 5. I will write it as in the numerator, it becomes z raised to 5, replacing this one. But this limit is 1 as z tends to 0. And as z tends to 0, this becomes cos z. Cos 0 is 1. As z tends to 0, this becomes minus a. And this becomes b square to the power 7. Isn't it? So it becomes 1 upon minus a into b to the power 14, which is again L, that is bounded. Therefore, you are multiplying by z raised to 4. Therefore, z equal to 0 is a pole of order 4 of this given example. F of z has a pole at z equal to 0 of order 4. Now at z equal to plus or minus k pi also, because sin pi is again 0. Sin pi is again 0. That we are saying z equal to plus or minus k pi, z minus plus or minus k pi to the power 5, multiplying by this term, and sin raised to 5z. So as z tends to k pi, this numerator and denominator becomes 1. So I am putting k pi. So its limit becomes 1. We get plus or minus k pi cos plus or minus k pi square upon 2a minus a plus or minus k pi and k square pi square plus b square to the power 7. This is also some finite. Therefore, we can say that f of z has a pole at z equal to plus or minus k pi of order 5. So in above example, we say that z equal to a is a pole of order 1, z equal to plus or minus ip is a pole of order 7, z equal to 0 is a pole of order 4, and z equal to k pi plus or minus k pi is a pole of order 5. Okay, that is the case. Same way, observe that the condition limit as z tends to 0, z minus z0 to the power n, f of z not equal to 0 is equivalent to the condition that n is the smallest positive integer such that z minus z0 to the power n, f of z has the removable singularity at z0. Okay, that is the same. Because for removable singularity also, limit of that function must be exist. Thus, if f of z analytic in a deleted neighborhood of z0, then f has a pole at z0 if and only if there exists an n such that z minus z0 to the power n f of z is bounded near z0. More precisely, f has a pole of order n if and only if this limit is not equal to 0 and z minus z0 to the power n f of z has a removable singularity at z0. That is limit as z tends to 0. We are multiplying, if I multiply z minus z0, then it should be equal to 0. Okay. We have one more remark. If f of z has a 0 of order n at z0, means f of z has a 0 of order n at z0 if and only if 1 upon f of z has a pole of order n at z0. We know that. When we say that f of z has a 0 of order n, if it can be written as z minus z0 to the power n into g of z. Right? What will be, this is f of z. What will be 1 upon f of z? 1 upon z minus z0 to the power n g of z. And here in this case, if I multiply this by z minus z0 and take limit as z tends to 0, z0, then it will not be equal to 0. You will get some limit. Therefore, 1 upon f of z has a pole of order n there. Okay, that is the remark there, no doubt. That we have proved here. Same thing is there. Now, let f of z is sine of z square, then f of z has a double 0 at z0 equal to 0. Or z equal to 0. It is double 0 because sine of z square is there. So 0 of order 2 is there. Then f of z has a double 0 at z0 equal to 0 and simple 0 at zk equal to square root of pi k. Square root of pi k, because it has a 0 at z square equal to pi k also. If I take z square equal to 0 is also 0 and z equal to pi k, z square equal to pi k is also a 0. Therefore, pi k square root of pi k is a simple 0, but 0 is the double 0 of that, because f of zk is 0 and f dash at zk is equal to f of zk becomes 0. And if I find its a derivative, what will be f dash at z? cos of z square into 2z. So f dash at zk becomes 2zk cos of zk square, which is not equal to 0 for k not equal to 0, for k not equal to 0. And so f of z0 is 0, but f dash at z0 is not equal to 0. So 1 by f of z has a double pole at z0 and a simple pole at zk. Note that the Laurent expansion for 1 upon f of z in 0 less than mod z less than root pi contains even powers of z only. We have this result there. Let n be a deleted neighborhood of z0 such that f is analytic in n, deleted neighborhood in analytic in deleted neighborhood. So suppose that deleted neighborhood of z0 means what? Suppose z0 is here. We are removing this one point only, and the remaining neighborhood is called deleted neighborhood. If f has an isolated singularity at z0, then z0 is a pole of order n if and only if there are positive constants c1 and c2 such that z minus z0 to the power n of f of z lies between c2 and c1 for some deleted neighborhood n0 of z0 such that n0 must contain in n. What is this result? Suppose that n is a deleted neighborhood of z0 in which f is analytic. If f has an isolated singularity at z0, then z0 is a pole of order n if and only if this condition is satisfied. Suppose there are positive constants c1 and c2 satisfying this condition for some deleted neighborhood n0 of z0 such that n0 containing n. Now we want to show that this z0 is a pole of order n. Then z minus z0 to the power n f of z is bounded. It lies between these two numbers means what? It is bounded for points near z0. If this is bounded means what? Limit of this function exists, it is equal to k. And if I multiply this with again z minus z0 and taken its limit as z tends to z0, this is going to be 0 as z tends to z0. Right? So limit of z minus z0 to the power n plus 1 of f of z is 0 as z tends to 0. That is, mod of z minus z0 to the power n f of z is greater than or equal to c2 as z tends to z0. This is approaching to 0 means what? It should be greater than or equal to something c2. So we have considered this is less than or equal to c2. Thus, by theorem, if f is analytic in a deleted neighborhood of z0, then f has a pole at z0 if and only if there exists an n such that this is bounded near z0. Thus, z0 is a pole of order n for f. This is applicable. Conversely, suppose that f has a pole of order n at z0, then z minus z0 to the power n f of z is bounded for points near z0. So by removability theorem, Riemann's removability theorem, there exists bounded point near z0 means what? There exists a function g which is analytic at z0 such that g of z is equal to z minus z0 to the power n f of z in some deleted is analytic in some deleted neighborhood n0 of z0. If g were such that this holds with g bar analytic at z0, then g bar of z is equal to z minus z0 to the power n minus 1 into f of z in n0 and is bounded near z0. This contradicts the fact that z0 is a pole of order n because this will not happen. As it is pole of order n, z minus z0 to the power n of f of z must be bounded. Thus, it is unbounded near z0 and therefore there are constants c1, c2 such that this z minus z0 to the power n f of z lies between c2 and c1 for some deleted neighborhood n0 of z0 such that n0 is contained in n. We have one remark from that. If f is analytic in a deleted neighborhood of z0, then z0 is a 0 of order n if and only if there are finite positive constants c1 and c2 such that this function lies between c2 and c1. Nothing else. We have taken minus n, there was plus n. And therefore this condition is reversed there, multiplying both sides to the power minus 1. If we take the reverse order. So if a by b is less than c by d, then we know that b by a is greater than d by c. That we have used, nothing else. Okay. Then this is also one important result. If f of z has an isolated singularity at z0, then f of z has a pole at z0 if and only if limit as z tends to z0 of f of z equal to infinity. That means it is singularity. If f of z has an isolated singularity at z0, then f of z has a pole at z0 if and only if limit as z tends to z0 f of z equal to infinity. First of all, suppose that f has a pole of order n at z0. Then f of z can be written as z minus z0 to the power minus n g of z if it is a pole of order n, where g is analytic and is non-zero at z0, right? Because that can be written as f of z upon z minus z0 to the power n. And if I multiply it with z minus z0 to the power n and find its a limit, then it becomes z at g at z0, which is non-zero at 0 and analytic. By continuity of g at z0, there is a neighborhood n of z0 on which f is defined except at z0, and mod of g of z, right, is greater than or equal to mod of g of z0 divided by 2 for z belongs to n. Hence, mod of f of z, which is nothing but mod of z minus z0 to the power minus n g of z, and this is greater than or equal to g of z0 into z minus z0 to the power minus n upon 2. Because gz is continuous, by continuity of g at z0, right, there is a neighborhood n of z0 on which f is defined except at z0, and this is by using z is continuous, right? This is by using z is continuous. Hence this holds for n belongs to capital N except 0 z0, that is limit as z tends to z0 of mod f of z equal to infinity, that is unbounded. Okay, that is the case there. So this proves if f of z has a pole at z0 of order n, then this is equal to infinity. Conversely, suppose that f has an isolated singularity at z0 such that limit as z tends to z0 of f of z equal to infinity. Then for a given epsilon equal to 1, there exists a delta greater than 0 such that mod of f of z greater than epsilon, which is equal to 1 in this deleted neighborhood. Limit is infinity means what? We know that limit is definite means what? This mod f z minus L should be less than some number, and limit infinity means what? As z tends to z0, mod of f of z is greater than any number, means increasing and increasing. Consequently, the function 1 upon fz in this case becomes analytic and bounded on puncture disk, this one. Because if mod fz is greater than 1, then 1 upon mod fz will be less than 1. That it is analytic as well as bounded in this disk. With limit as z tends to 0, 1 upon f of z equal to 0. So by Riemann's removability theorem, it follows that 1 upon f of z has a removable singularity at z0. Has a removable singularity at z0. Now, if and so removable singularity means what? We can remove it. We can remove the singularity by redefining the function. So let gz equal to 1 upon f of z and 0 for z equal to z0. What will happen? Then g is analytic in a disk having center at z0 raised at and radius delta. Clearly g is not identically 0, but gz has a 0 at z0. Therefore, it follows that there exists a natural number such that gz equal to z minus z0 to the power n into psi of z. Identically, it is not identically equal to 0, but has a 0 of order something. So it can be represented in this way, where psi is again analytic and non-zero at z0. As psi at z0 is non-zero and gz is also non-zero, on this disk we have fz equal to 1 upon gz, 1 upon this one, that is phi z upon z minus z0 to the power n, where phi z we have taken 1 upon psi z, which is analytic at z0. Hence, limit as z tends to z0 of f of z into z minus z0 to the power n equal to, if I multiply by this with z minus z0 to the power n, then your limit becomes only limit as z tends to z0 of phi z, that is phi at z0, which is not equal to 0. Therefore, what this implies? This implies it has a pole of order n. This shows that f has a pole of order n at z0. So this is the again important result. What result says that an isolated singularity is a pole of order n if and only if limit as z tends to z0 f of z is infinity, isn't it? It is infinity. One more remark is there. If f has an isolated singularity at z0, then fz has an essential singularity at z0. Now, before we go, I will go for this essential singularity. Essential singularity which is not removable. Not removable. That means essential singularity. The singularity which cannot be removed, which is essential singularity, isn't it? So f has an isolated singularity at z0. So there are two types of isolated singularity. Main two types, isolated, non-isolated. Then for isolated, removable and essential. So removable means the limit at z tends to z0 of this function exists, removable. And if it not exists, it is not removable. Therefore, such type of singularity are called essential singularity. So if f has an isolated singularity at z0, then f of z has an essential singularity at z0 if and only if limit at z tends to z0 of f of z fails to exist, either as a finite value or as infinite limit. So limit of this term does not exist, then it is called essential singularity. Then we call it as essential singularity. For example, e to the power 1 by z. Z equal to 0 is the essential singularity of e to the power 1 upon z, because limit of e to the power 1 by z as z tends to z0 does not exist. Such types of singularities are called essential singularity. So this is about singularities. Now in all singularities, what we have done? A regular point and singular point. A function is said to be regular at z0 if it is analytic at z0. If it is not analytic at z0, the point is called singular point. Then for singular, we have again two types. One, isolated. Second, non-isolated. Isolated means except that point, singular point, if there exists a neighborhood in which the function is singular, analytic, then it is called isolated singularity. And non-isolated means for every neighborhood of that singularity, there are again singularities in that neighborhood, so that this singularity is called non-isolated. For example, suppose z0 is the singularity of this function and in this neighborhood. So if except z0 for every point around this, if the function is analytic, then this singularity is called isolated. And for every neighborhood of z0, there are again one more singularity, then we say that z0 is non-isolated. For isolated singularities, we have two types. One, removable, and second one, essential. We know that the meaning of essential, meaning of remove, which can be removed, which cannot be removed. It should be. That is called essential. And removable means can be removed. So when we say that the singularity is removable, if limit as z tends to z0 of f of z exists, or f of z is bounded near z tends to z0. And what about essential? If this limit does not exist. So singularity, but limit does not exist. And pole is also there. Pole is also isolated singularity. When we say that pole, if limit as z tends to z0, z minus z0 to the power n, f of z is exist and not equal to 0, then we say that this has a f has a pole at z equal to z0 of order n. So this n must be smallest. So this is the about classification of singularities. Classification of singularities. And its example we have discussed in this. Okay, 2-3 lectures we have discussed their examples also. So we'll stop here. In next lecture, we will see again a technique to see whether the function is having singularity or regular or which type of singularity there. Okay, so for this lecture we will stop here, and next lecture we will see next time.